Hi everyone, today we're going to take a look at some applications of sinusoidal functions not involving angles for many of these. So in our previous lesson, we learned about applications involving rotations, but there are many other periodic motions that we can track as long as they regularly return to their previous values over a consistent speed or time limit. That can be considered periodic. Something that we could look at is potentially like temperature over the seasons, right? Those kind of regularly return back. It's not like perfect because we know we have temperatures that are different on different days, but those kind of regularly return as we hit summer, fall, winter, and spring. One thing that's like maybe more perfectly periodic is the distance of the Earth from the sun over like at a particular location, let's say in Oakville, Ontario. What's the distance from Oakville to the sun at particular times? That will always be relatively consistent as we kind of rotate around the sun for a year. So yeah, we're going to take a look at things that have to do with periodic motion that aren't necessarily rotations. They could be height and time, or like I said with the sun, distance versus time of the year. We could take a look at tides and see like over a 24-hour period how tides can change, height of tide versus time, things like that. So in this case, we're going to take a look at a Ferris wheel, which we did look at in our rotations lesson, but in this case we're going to do time in seconds as our x's and height above the ground as the rider rotates around the Ferris wheel. So I've labeled height in meters as my y scale and time in seconds as my x, and I've also labeled these out. So you might be wondering kind of how I came up with these numbers here, and I'm going to show you how I did that. So firstly, I calculated the maximum, which was c plus the amplitude, and that gave me a maximum of 22 meters. So the rider is going to hit a maximum height of 22 meters above the ground. And I also calculated the minimum by doing c minus the amplitude, and that told me that the rider was going to hit a minimum of 2 meters above the ground. So I wanted to make sure that my y scale could accommodate that. And for the x scale, I figured out the period of the function, which we can do by doing 360 over our k value, which is 3. And I got 120. And in this case, this means 120 seconds. So this little space right here, that should give me enough to graph a full cycle. And then I did a couple more little points there. You can fill out the whole thing if you want. I just went by 15s. So the next one would be 180 and then 195. So we're gonna plot that out. And then I want to take a look at kind of a little trick that we can use to figure out how to graph this without necessarily having to do transformations. So if you've got your x and y axis kind of labeled out here, one route that we could take to graph this function is certainly taking our parent function sine x, and if you want, you could take y equals sine x, and you can graph out the parent function points as we have done in previous lessons, and you can do transformations. So if you did transformations here, we would be doing 1 over k times x plus d, and then we would be doing 10y plus 12. And then you would essentially take each of those points and do your transformations. But I want to show you a little trick to graphing these as well that you can use in your transformations. And that is, let's start with the midline. Okay, that's the c value. You're just going to sketch that out with a dotted line here. And you're going to plot the d of sine, which is 30 to the right. This is actually the rising midline. And so I'm going to trace along this C line until I hit 30 to the right, and that will be my first point. Now, because I know that the period is 120 seconds, I know that 120 seconds after 30, which is at 150, I'm going to hit the same point again. So that's going to be one full cycle that fits between 30 and 150. And our rising midline is going to be rising up into a max. So my thought is that we're going to have kind of something like this. Don't draw this yet. Where I have another midline somewhere around here, a minimum and a maximum. So I want to kind of figure out where those are. So let's start with this middle point here. This middle point needs to happen exactly halfway between 30 and 150. And if you're not sure exactly where that is, I mean, you can kind of probably eyeball it and see, but you can do 30 plus 150 divided by 2 to find their center. It's kind of like finding the average of those two values. And that would actually give you 180 divided by 2. That tells us that that next midline or center value is going to hit at 90. Now, the maximum is going to happen exactly halfway between 30 and 90, which is 60. And our maximum point is up at 22 because we found that here. So there's our max. And our minimum is going to happen exactly halfway between 90 and 150, which is 120. And our minimum was 2. So I'm going to have a point at 2. So I could actually kind of extend this in the backwards direction as well. If I know that I'm kind of coming down here to 120, I can use that kind of idea and extend my graph in the backward direction as well, because I can kind of see that I'm going by 30s. And then we'll just complete our cycle here. So basically this is one full cycle without this point here. But you can, of course, graph more. But if you were just asked for one cycle, that's essentially what we would be graphing right there. So this is a really great little trick to help you with graphing your function without necessarily having to do all the calculations. But if you did do calculations here, I think you would find that you're getting basically the points that we just graphed. So you were getting like 30, 60, 90, 120, 150. And then you would have found that you got 12 for each of these, and then 22 and 2. Yeah, so that's what your graph should look like. So either way you do that, you can do the regular transformations if that's what you feel comfortable with, or you can use that little trick. So part B, we've already really determined all these things. We figured out that max is 22 meters, min was 2 meters, and the time for one revolution, or in other words, the period, it takes 120 seconds. I just spelled that wrong. And height of the rider after 30 seconds, we can see that that is clearly 12, and we can see that on our graph here as well. So after 30 seconds, height is 12 meters. Okay, express the equation from example 1 as a cosine function. So this is h at t. Remember, to change into a cosine function, all we need to do is find the location of the maximum. And we can actually see that that occurs 60 seconds to the right of the y-axis. So I'm basically going to keep my sine function the same, except I'll change it to a cosine function. And then I'm going to change the shift to negative 60 here. There we have it. Okay, let's take a look at another application. So the height of a tide on any given day, t hours after midnight, is modeled by our function h at t, and this is modeled with a sine function. We are going to find the max and min values for the depth of the water. So max and min, we can find these really quickly by simply doing c plus amplitude and c minus amplitude. So our c value is 7 and our amplitude is 5, which means that the max height of the water must be, probably should have said in meters. So this will be 12 meters. And for this one, we'll do 7 minus 5. So our minimum height will be 2 meters. What time is high tide and what time is low tide? So there's a couple ways that we can solve this one. I can actually take these and I can plug them in for h at t and try to solve the equation. But what I really like to do is actually just take the parent function which in this case is sine, and I'll do the transformations. And you'll notice that because the parent function of sine, let's say f at x equals sine x, it contains maximums and minimums in it, that the maxes and mins of the regular sine function, which will basically be the 1 and -1 point, those will actually transform into the max and min of our transformed function. So we have the points 90, 1, and 270, -1. Those are really the only points that I kind of need to focus in on here. So if I do my transformations, I'm going to get 1 over 30 times x plus 5 and 5y plus 7. And I'm just going to look at 90 and 270 for this one to see where these guys transform to. And that should give me, the y's will give me the maximum height, and the x's will give me the times at which these occur. So 90 times 1 over 30 is actually 3, plus 5 is 8. And then 270 divided by 30 is 9, plus 5 is 14. And 5 times 1 plus 7 is 12, as we expected, and 5 times -1 plus 7 is 2. So remember, the x's here are representing height in meters. The x's are representing time after midnight, and the y's are representing height in meters. So the max of 12 meters occurs at 8 hours after midnight. That's 8 a.m. And leave a little space there. So we're going to come back to that in a second. Minimum of 2 meters occurs 14 hours after midnight. So that's actually 2 p.m. Now, what you really need to ensure here is that the max and min don't occur multiple times in the day, because there might actually be other times where we hit max and min values. So in order to ensure that, you're going to find the period of the function. We're going to do 360 over k. And that's actually going to give us a period of 12 hours, which means that every 12 hours I'm going to hit a max, and then every 12 hours I'm going to hit a min. So if I add 12 hours to this, that's actually 8 p.m. as well. That has a max value. And then same thing here. If I add 12 hours, that's going to be at 2 a.m. And that will also be a time where we hit a minimum tide. So always check the period. And if you have multiple times during the day where you can hit a max or min, make sure you include that in your answer. Okay. And finally, the last part of this asks us, what is the depth of the water at 9 a.m.? So 9 a.m. is 9 hours after midnight, which means that we will essentially just evaluate, sorry, this looks pretty awful. We will essentially just evaluate h at 9. So I'm going to plug that into our function here. Oops. So 9 hours after midnight. And we are basically just going to plug this right into our calculator, making sure we're in degree mode. So plug that in and calculate. Make sure you're doing order of operations. So simplify this, do sine of 120 times 5 and then add 7. And you should get about, let's say, approximately 11.33 meters. Okay, this should also kind of make sense because an hour earlier at 8 a.m. I'm at a maximum tide of 12 meters. So an hour later makes sense that I should be still close to 12, but less than 12. The tide is kind of going out after that. All right, and for our last example here, we are going to take a look at a wind turbine. We're going to take a look at a wind turbine, and we're going to actually do degrees with this one. So we're going to track the height of a blade as it turns around the wind turbine. So I'm talking about those big windmills that you see with wind energy, harnessing wind energy. And let's just draw a picture of what we have here. So I have a wind turbine, And that's the center of it. Here's our ground. And I've got a blade, and that blade is essentially going to be kind of like rotating around. It's going to make a circle. So basically it says that assume this blade starts at 0 degrees. So I think this kind of means like our normal 0 degree location, which is going to be here. Okay, so this is going to be 0 degrees, and as our blade kind of turns around here, it's going to go counterclockwise, then it's going to be here, and then it's going to go to the next location, which will be an important location, so then it will be here, and then finally it will go down to this location here, and it's going to be here, and then it will rotate, of course, back up to its normal position there. So we kind of need to figure out, as that blade is turning around, if this is the 0 degree mark, then of course each of these is going to be 90 degrees from that mark. So we can just kind of put those in right now. That'll be 270 and 360. And we need to figure out the heights here. So if the wind turbine has a height of 55 meters to the center, I know that this height right here is basically going to be 55 meters. So at this height for both of these, I'm going to be at 55 meters here and also here. Okay, and then the blade is 10 meters. So if I go 10 meters up, so this is another 10 meters right here. So if I go 10 meters up, basically that height from the ground is going to be 55 to get to the center, plus an extra 10, and that's going to give me 65 meters. And similarly, if this is 55 and I subtract the height of the blade, that's actually going to give me a height of 45 meters. Okay, so we have each of our heights above the ground at each of these important locations. So let's just kind of, I'm just going to clean this up a little bit. Okay, so here's my start position. Now I'm going to do a little trick here, and that is we're just going to kind of shrink this piece of the x-axis down a little bit, because we really only want to go between 45, 55, and 65. So that would take me a little bit too far to go by like 5s all the way up. And this way we can essentially just do like 40, 45, 50, 55, 60, 65, just so we can get kind of like a zoomed in version. So this just basically means we're taking the bottom part of that x-axis, or y-axis rather, and kind of shrinking it down. We're kind of like crunching it. And this is going to be our rotation in degrees. Okay. So starting position is going to be 0 degrees. What is our height at 0 degrees? Well, our height at 0 degrees is 55 meters. So at 0, we're going to be at a height of 55 meters, and that's where we'll start here. Now we're going to rotate. We're rotating counterclockwise. We're going to rotate to our next important position here, and that's going to be 90 degrees. So at 90 degrees, how high are we above the ground? Well, we already figured that out. We figured out that we are 65 meters above the ground. So now at 90, we'll be at 65 meters. Plot that here. Okay, and we'll rotate to our next position here. So now we're at 180 at a height of 55 meters above the ground. Let's plot that. Okay, next location, we are now 270 from where we started, and we're at a height of 45 meters above the ground. Remember, this is just the tip of the blade, so this is literally like these tip positions that we're kind of tracking around here. So plot 270, 45, and then finally we're going to rotate back up to our starting position. So at 350, we'll be back at 55 meters. 360, sorry. Okay, and there we have it. So there's our graph of our function. And I would also like to ask you, what is the equation of this function. So perhaps we can use h at x for this one. And we are going to know the amplitude of this based on the radius of this circle. So if the blade is 10 meters long, I know that my amplitude is 10. Period here is 360, so k needs to be still equal to 1. Our sine value shift, our rising midline is actually on 0 here. So what we can actually do is leave the x inside sine here, and our c value is the midline. So you can actually even visibly see it on the graph here. Our midline is this kind of center height in here, and that is 55 meters. So here is our function that represents this graph.